In this video, we're going to get some practice working with sequences. Let's look at example 1. List the first 5 terms of the sequence. Part A sub n equals 1 minus 0.2 to the n. We could proceed with this immediately using decimals, and that's fine. Let's instead rewrite this using fractions. So we have 1 minus 1/5 to the n power. So a sub 1 is going to be 1 minus 1/5 to the first power, which is 4/5. A sub 2 is going to equal 1 minus 1/5 to the second power, which is 1 over 25, which equals 24 over 25. A sub 3 will equal 1 minus 1/5 to the third power, which is 1 over 125, giving us 124 over 125. A sub 4, 1/5 to the fourth, is going to give us 1 over 625, and that will give us 624 over 625. And finally, a to the 5th is equal to 1 minus 1/5 to the 5th. Now, 5 to the 5th is 3125. So we're going to get 3124 over 3125. Going on to part B, a sub n is equal to 3 times negative 1 to the n power over n factorial. So a sub 1 is going to give us 3 times negative 1 to the first over n factorial. Negative 1 to the first will just give us a negative 1 times our 3. 1 factorial is just 1. And so we start with negative 3. A sub 2, 3, negative 1 squared. 2 factorial is 2 times 1. The top becomes positive, and the bottom is just 2. A sub 3, we have 3 times negative 1 to the third power over 3 times 2 times 1. That's 3 factorial. In the numerator, we have negative 3. In the denominator, we have 6, which reduces to negative 1/2. A sub 4, we have 3. Now, we might be noticing that anytime we have an even exponent here, we're going to get a positive. So I'm just going to leave that as 3 times a positive 1, just as 3. And on the bottom, we have 4 factorial, which is 4 times 3 times 2 times 1. And that's going to give us 1 over 8. A sub 5, this time the numerator will be negative, so we have negative 3, and on the bottom we have 5 times 4 times 3 times 2 times 1. The 3's cancel, we get a negative 1 on top, and on the bottom we have 40. Example 2, find a formula for the general term a sub n for each sequence, assuming that the pattern of the first few terms continues. So looking at the first one, we have 1's on top, so a sub n is going to equal 1 over, and on the bottom we have powers of 2. We have 2 to the first power here, 2 squared, 2 to the third, etc. So we get 2 to the n in the denominator. Part B, 2, 7, 12, 17. So here we hopefully notice that we're adding the same quantity here, plus 5 each time. So b sub n is going to equal 2 plus 5. Now, that's how we get our second term. So when we plug in a 2 for n, because that's our second term, we want this quantity to equal 1, so we get 2 plus 5. So we can put in n minus 1. If you plug in 1 here, you're going to get 0. 5 times 0 is 0, and you just have the 2. If you plug in 2, you're going to get 5 times 1 added to the 2, which gives you 7. If you put in 3, you'll have 2 plus 5 times 2, which will give you the 12, etc. We can rewrite this by distributing the 5 to get 5n minus 5, but then when we add 2, we get minus 3. Now try plugging in 1, then 2, then 3, then 4, and you should get each of the terms in the sequence above. Part C, we have 1, negative 2/3, 4/9, negative 8 over 27. So first off, we notice that we have alternating signs. So we're going to need -1 to a power. Now if we just put n here, that means our first term, when we plug in 1 for n, is going to be negative, and we don't want that. So let's go ahead and put either n plus 1 or n minus 1. I'm going to put n minus 1. Now the numerators start with 1, then 2, then 4, then 8. Those are powers of 2. So if we put 2 to a power here, again, if we put n, that's not going to work because when n is 1, we're going to start off with a 2, and we don't want that. So we put n minus 1 as well. Now, when we plug in 1, we get 2 to the 0, which is 1. We plug in 2 for our second term, we have 2 to the first power, which is 2, etc. In the denominator, we have powers of 3. So similarly, we're going to write this. You can pause the video and plug in values to check. Now, because each base has the same exponent, we can rewrite it this way. Again, pause the video, plug in the values 1, 2, 3, and 4 in for n, and you'll see that it gives you that sequence. Example 3, determine whether each sequence converges or diverges. If it converges, find the limit. Part A sub n equals n over n plus 1. Here let's just jump in and try to get the limit as n goes to infinity. We can multiply both numerator and denominator by 1 over n. On top we get a 1. On the bottom we get 1 plus 1 over n. Now if we let n go to infinity, we're going to get 1 over 1 plus 0, which is 1. So a sub n converges. Part B, a sub n equals ln of n over n. With this one, we notice that as n approaches infinity, both the numerator and denominator go to infinity. And so this might make us think of L'Hopital's rule. However, we can only use L'Hopital's rule with functions. So we're going to start off by letting f of x equal ln x over x. So now we look at the limit as x approaches infinity of ln x over x. We're going to apply L'Hopital's rule because we have infinity over infinity. This becomes the limit as x approaches infinity of 1 over x over 1. And now the numerator goes to 0, and we have it. Part C, a sub n equals 4 to the n over 5 to the n plus 1. So we can rewrite this as 4 to the n over 5 times 5 to the n, which is the same as 1 over 5 times 4 over 5 to the n. Now, if we take the limit as n approaches infinity of a sub n, that's the limit as n approaches infinity of 1 over 5 times 4/5 to the n power. Using limit laws, we can bring the 1/5 out. Now here we can use a theorem that we proved in class. If we have a sequence r to the n, and we're taking the limit as n goes to infinity, then that limit equals 0 whenever r is between -1 and 1. And that's exactly what we have here. So this becomes 1/5 times 0, which equals 0. So a sub n converges. Part D, a sub n is equal to -1 to the n over n. Here we have an alternating sequence. The terms of the sequence are -1, +1/2, negative a third, positive a fourth, negative a fifth, etc. So we're going to start off by looking at the limit as n approaches infinity of the absolute value of a sub n. That, of course, is going to make all of our terms positive, so we end up with the limit as n approaches infinity of 1 over n, which is equal to 0. Now we recall this theorem, which says that if the limit of the absolute values of our sequence as n approaches infinity equals 0, then the limit as n approaches infinity of the sequence itself also equals 0. Part E, the sequence 3 plus the quantity negative 1 to the n power all over n squared. It might be a little unclear how to start with this one. So first, let's just notice a couple things. Every term of our sequence is bigger than 0. Also notice that the numerator is never larger than 4. It could equal 4, but it's never going to be bigger than 4. So now we have this three-part inequality. If we take the limit on all three sides as n approaches infinity, it's going to look something like this. The limit on the left is 0. And the limit on the right is also 0. So by the squeeze theorem for sequences, we've shown that our sequence converges to 0. Part F, the sequence square root n plus 2 minus square root n. Here we're going to start off by borrowing a technique from our work with limits back in Calculus 1. We're going to multiply top and bottom by the conjugate. And that will give us a fractional representation of our sequence that we can then work with. Much like in the previous problem, notice that every term in our sequence is going to be greater than 0. Also notice that every term in our sequence is going to be less than 2 over the square root of n plus the square root of n, because this denominator is bigger than this denominator for all n greater than or equal to 1. Of course, we can rewrite this side as 2 root n in the denominator, which is 1 over the square root of n. Now we'll take the limit on all three sides as n approaches infinity. Both the right and left-hand limits are 0. So our sequence converges to 0 by the squeeze theorem. Part G, a sub n is equal to n factorial over 2 to the n. If we expand out our a sub n term, it'll look something like this. Now, if we split up this product into the product of the fractions, we get this. Now, we're going to compare this to a simpler sequence. Notice that we have 1/2 here, and here we have n over 2. And then we have all these positive factors in the middle that are all greater than or equal to 1. So this product has to be greater than or equal to 1/2 times n over 2. In other words, if you just take the first and last factors of the left-hand side, that product, which I've written here, has to be less than or equal to the left-hand side. This, of course, equals n over 4. Now, since n over 4 approaches infinity as n approaches infinity, and a sub n is greater than or equal to n over 4, since the smaller sequence is diverging to infinity, that means that the larger sequence must also diverge. Example 4, determine whether the given sequence is increasing, decreasing, or not monotonic. Is the sequence bounded? Part A sub n is equal to 1 over 2n plus 3. First, let's take a look at a sub n plus 1, and we'll compare that to a sub n. Now, 2n plus 5 is going to be larger than 2n plus 3. And if the denominator is larger, that makes this fraction smaller. So for all n greater than or equal to 1, we have that a sub n plus 1 is smaller than a sub n, so a sub n is decreasing. Also, notice that a sub n is always greater than 0, but it's also less than or equal to 1/5. When we plug in 1, we obviously get 1/5, and then after that, every subsequent term is smaller, so every term in our sequence is less than or equal to 1/5. So a sub n is bounded. Now, by the monotonic sequence theorem, every bounded monotonic sequence is convergent. So a sub n is convergent. Part B, sine n pi over 2. If we look at the first few terms, we'll notice that we get sine of pi over 2 when we plug in 1, sine of pi when we plug in 2, sine of 3 pi over 2 when we plug in 3, and so on and so forth. Evaluating each of these, we get 1, 0, -1, 0, 1, and then this pattern will continue. So this sequence is bouncing between 1, 0, and -1. So it is neither increasing nor decreasing, so we say that it is not monotonic. However, it is bounded between -1 and 1. And we can write that as the absolute value of sine n pi over 2 is less than or equal to 1. Part C, a sub n equals n over n squared plus 1. With this one, let's go ahead and define f of x as the function x over x squared plus 1. Now let's look at f prime. Using the quotient rule, we have x squared plus 1, the bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 2x, all over the bottom squared. And this simplifies to 1 minus x squared over x squared plus 1 squared. Now notice the denominator is always positive, but for x is greater than or equal to 1, the numerator is always going to be negative. So we have that this is less than or equal to 0 for all x greater than or equal to 1. Well, if we know that the derivative is negative, that means the function is decreasing. So our sequence is decreasing. Now looking at the sequence again, notice that a sub 1 is 1 over 2. And the sequence is decreasing, so 1 over 2 must be the largest value. Also notice that a sub n could never equal 0 or be negative. So we've noticed that 0 is less than a sub n is less than or equal to 1/2 for all n greater than or equal to 1. Therefore, a sub n is bounded. Go ahead and do the rest of the problems in the worksheet in a similar manner.